Okay, hi everyone. This is going to be a lesson on 2.3 trigonometric graphs. And I'll remind you that where we left off with trig is so far we've learned what the 6 trig functions are. We've learned how to evaluate them with little examples like this. But in math, whenever we learn about new functions, we always like to talk about what do the graphs look like, and a couple of other things like what's the domain and range, what are these functions used for, do they have inverse functions? So some of the same things that you've seen with other functions. All right, so this first example is not really the graphs yet. This is just kind of like a warm-up problem. And if you'd like, you could pause the video and try this one on your own. But I'm going to talk about this. You know I like to do a little scratch work unit circle for these. And we've done problems like this. In fact, we might have actually done sine of pi over 2 already in previous section. You know that we start at the usual spot. We go a distance of pi over 2 around the unit circle, and we figure out what terminal point it takes us to. And, you know, the point that this takes us to is 0, 1, but what we really want for sine is just the y-coordinate. So sine of pi over 2 equals 1. The next one, and maybe you can tell that I have these set up like this for a reason. The next one I've set up to be 2.5 pi. So that's 2.5 pi, and part A was just half of pi. So remember, 2 pi takes you all the way around the unit circle. So if it's 2.5 pi, then you go all the way around the unit circle, counterclockwise, and then you still have to go half of pi. So in the end, it takes us to the same terminal point. And if it's the same terminal point, then it has the same sine value. Okay, so this is maybe a little reminder that sometimes you could have two different t values that when you put them in, they have the same terminal point, and therefore they have the same sine. Well, I guess that means that they're going to have the same cosine also, right? So up here, I wrote the terminal point was 0, 1. So for cosine, you use the x-coordinate of the terminal point. So same point, cosine of it is 0, and then cosine of 2.5 pi, we've gone around the unit circle an extra lap, but we're still arriving at the same place. Now, if you wanted, you could keep going around the unit circle again and again and again. And the idea is that these are functions that keep repeating themselves. In fact, you could say they repeat every 2 pi. So that brings us to this note down at the bottom of the page. We have a name for that kind of behavior. We say sine and cosine are periodic functions, and that they have period 2 pi. So basically, they repeat themselves every 2 pi. And that's kind of shown here that if you add 2 pi to t, you get the same result. And the same thing for cosine. It's like you've gone around the unit circle an extra time, but you're still arriving at the same sine and the same cosine. So it seems like this idea of a function being periodic, that it like somehow repeats itself, it should show up somehow in the graph. And that's not something that we've seen with other graphs. Like when you do graphs of exponential functions or log functions or, you know, parabolas, none of those are periodic. So this is something interesting about trig functions. The key idea is that we'll investigate their graphs by referring to values we know from the unit circle. So I think I have to move the whole page away in order to get my new page to fit. So we'll do a little reference unit circle. Let's see, how many points do we want to label on this? Why don't we just start with some points and, how much of this can I fit on the screen at once? All right, here's what I'll do. The graph of sine, I'll try to fit that up here. And what I was going to draw down here, I'd really like to fit it on the screen next to the unit circle. So I'll try to do that up here. Graph of sine All right, so we're going to draw sine in more than one graph on this page. You can see that there's some room at the bottom for kind of a zoomed out picture. So what I would like us to do is have a horizontal axis be the t-axis, because usually we've been doing something like y equals sine of t. So what we're inputting into the function is t, and I guess we should label some things on each axis. So I know that 2 pi seems like it's pretty important for trig functions, so let's put 2 pi somewhere. And then halfway to that would be 1 pi. Halfway to that would be pi over 2. So I'm just kind of putting some of the values that might be important. And then over here, in between pi and 2 pi would be 3 pi over 2. I mean, that's 1.5 pi. So if you think about it, when we're about to graph, this is us graphing sine, the largest value that sine would ever have would be 1, right? I mean, sine is going to come from a terminal point on the unit circle, and the largest y value we ever get is 1. So I think on my vertical scale, the highest up I need to go is 1, and the lowest I need to go is -1. So I guess I'm kind of doing these side by side, and I have my vertical scale kind of set up the same. It doesn't have to be set up at the same scale, though. All right, now we'll kind of add to the unit circle as we go, but just keep in mind that a unit circle is not a graph of sine. A graph of sine is going to look somehow a little different. So let's put some t values here. I know here's kind of a 0, pi, call that 2 pi, pi over 2, 3 pi over 2. I sometimes do the t values on the inside. We'll fill in more if we need them. So we just did a minute ago, sine of pi over 2 was 1, and that's because of this terminal point 0, 1. So on the graph, sine of pi over 2 needs to be 1. So we have a point on the graph up here. We're basically going to fill out a few points, and then we'll connect it with a nice smooth curve. We could do it with a table of values, but instead of a table, I'm just kind of using the unit circle. A couple of other common points we know. We know the terminal point 1, 0 over here. So it looks like sine of 0 is 0, right? So I could put a point here. When t is 0, sine is at a height of 0. And it looks like sine of 2 pi is also 0, so I could put a point here. Let's see. Let's do some other points we know. How about we'll do the easy ones first. So this over here is -1, 0. So sine of pi looks like it is 0. So when I go to pi, I need to have a point at a height of 0. I'll do the one down here. 0, -1. So sine of 3 pi over 2 is -1. So when I have my t value at 3 pi over 2, my point is down here. So we have 5 points on the graph so far. That might be enough for us to start to see the shape. It looks like it kind of goes up and then down and then back up. Let's fill in just a little bit more. I know that over here is pi over 4. We said that one is square root of 2 over 2, square root of 2 over 2. So, well, we need to know this as a decimal or something, right, in order to figure out where it goes on the graph. I'll tell you that square root of 2 over 2, here, square root of 2 is approximately 1.4. So square root of 2 over 2 is approximately 0.7. We don't need to know the rest of the digits, but I'll say that when my t value is around pi over 4, which would be about here, I would like to draw a point at a height of somewhere around 0.7. And we could kind of use similar reasoning to figure out some other points, like over here. That one's also at a height of around 0.7, so that point would be about here. So what do we have, 7 points on this graph so far? Okay, we could keep going with this and fill in all the points we know, and it would start to take shape. I think what I'll do is jump ahead a little, and I'll say that if we found these in-between points, they would be around negative 0.7. And now it's really starting to take shape. So I think what I'll do is maybe grab another color just to emphasize those were some points we found. The way that these get connected with a nice smooth curve looks something like this. This is if we found all the in-between points that we skipped. Some of those points are not the common values that we could find. But yeah, this is kind of the shape of the graph of sine. And it keeps going. I mean, it doesn't need to stop here. So maybe I'll just draw an arrow to sort of indicate in both directions it keeps going. Now, at the bottom of the page, I'm about to move the paper, and at the bottom we'll draw kind of a zoomed out version. So, zoomed out, what would this thing look like? Let's say I had 2 pi over here so that I have room to do kind of a 4 pi. And let's also go in the negative direction on this one. Well, the part of the graph that we drew kind of went up, down, back up again. And if we kept going, it sort of repeats the same shape again and again and again in both directions. And I'll draw an arrow on the left to say, yes, it keeps going, and an arrow on the right keeps going. So this idea that it keeps repeating the same shape over and over again, that's sort of what it means to be periodic, right? It's like you go around the unit circle, and then it just repeats itself. So on the graph, for every 2 pi that you go, the shape just repeats itself. It's almost like you could take the picture that we drew above and just sort of copy and paste it over and over. Like, here's a copy, here's a copy, here's a copy. Each one of those would be called one period. So before we move on to the next page, I just want to say that looking at this picture might give you a hint of what sort of things the graph of sine might get used for. It's really helpful for things in real life that behave like waves. I mean, we'll see some stuff later in the chapter, I think, where sine and cosine are useful for things that have to do with maybe water waves or sound waves or radio waves, anything that has this kind of waving up and down motion, but also some other things too, anything that kind of repeats itself. So we'll get to some of that stuff later. So the next page is going to do kind of the same thing we just did, but it's going to do it for cosine instead of sine. I think on that one I'm going to go a little faster since we've already done this one, and it's very similar. Okay, so we could do the same sort of thing for cosine and set up horizontal axis. I'm kind of focusing on just positive values of t for now, and then we'll do the zoomed out version after this. We'll put a 2 pi somewhere and some of the other values that we might use. We know these terminal points, 1, 0, 0, 1. These are a good place to start. 0, -1. Remember, for cosine, the thing that's different is we want the x values of the terminal points. So looking at this, I guess when t is 0, cosine of 0 is 1. So we need a point up here. Here, I'll point to it, this point. So the graph is already different, right? We're doing a graph of cosine t, and it already looks different than the graph of sine t. But that makes sense. They're not the same function. By the time t gets to pi over 2, cosine of that looks like it's 0, so we'll put a point there. Cosine of pi looks like it is -1, so we'll put a point there. Cosine of 3 pi over 2 is 0, so we'll put a point there. And cosine of 2 pi, 1 complete lap around the circle, cosine of that is 1, so we'll put a point at, looks like 2 pi comma 1. So those are 5 points, and it kind of almost looks like a V shape or a U shape. But before we connect it with sort of a smooth curved line, let's add a couple of extra points. So pi over 4, you know that cosine of that is square root of 2 over 2. We said that's around 0.7. So pi over 4 would be around here, and I want to draw a point at around 0.7. Doesn't have to be perfect, but we're just getting the idea across. Over here would be 3 pi over 4, and again, we're at, well, hold on a second. Let's see. This time we're at the negative something around 0.7. So 3 pi over 4 would be taking us down here. So it's not exactly a V shape. There's kind of a curve to it. All right, if we keep going, find a couple more points. I think the next points that we might work with would be 5 pi over 4, and this one over here is 7 pi over 4. And if you go with those, you're going to get negative root 2 over 2 here, positive root 2 over 2 here. So it's not exactly a U shape or a V shape. If we connect these with a nice smooth curve, it should look something like this. Now, remember, these functions just keep repeating themselves. So what happens as we go to the left or right is, I'll draw a little bit more of this one. This one comes down like that. This actually does look a little bit like the graph of sine, and it comes down over here. So we'll draw the zoomed out version in a moment. Just give you a chance to see that. All right, so the graph zoomed out. Again, the maximum height is 1, the minimum height is -1. Say that's 2 pi so that I can fit 4 pi over here to see more of it. So this one goes something like this. So when you draw these, try to draw it as sort of a nice smooth curve with kind of, gentle ups and downs. Don't draw it like a sharp zigzag, like a lightning bolt. Don't just like it's the letter V. It should be more like the letter U. So you know what? Let's compare the graph of sine and cosine. I think I might be able to fit these both on the screen. This was our page from earlier. So the one up top, this is the graph of sine. The one on the bottom is the graph of cosine. So they look very similar. They both have the same period. They're periodic functions, meaning they keep repeating. And, it kind of makes sense that they would look similar because think about how sine and cosine are related to each other. They both come from the unit circle. Just one of them is the y value, one of them is the x value. So it does make sense that there's kind of a relation there. One thing to remember, I guess, is that sine is the one that passes through the origin. So if you remember the overall shape of these, then you want to remember which one is which. This was y equals sine t, and it passes through the origin. And this one down here was y equals cosine t, and it's up here with a y-intercept of 1. So it kind of starts at the top of the hill and then goes from there. So at the bottom of this page, I think we have a note. Let's see what this says. It says we've been referring to t values, but we could also refer to trig functions as f of x. I mean, that's what we do in math a lot when we talk about functions, is we want them to be f of x. So we could do that for sine, cosine, and then, is this a t-axis or do we want to call this an x-axis, right? So it's just a different way of labeling it. It doesn't fundamentally change anything. It's just how it's labeled. So let's look at the next page. All right, this one is getting into some graph transformations. The truth is, I'm probably not going to ask you to just draw a graph of sine or just draw a graph of cosine. It's more likely that I would ask you something like this page, where it's kind of based on sine or cosine, but it's some kind of transformation. So remember, there is an appendix in the back of the workbook that has a page or two that goes over graph transformations. I'm just going to put a little note here that this is like the graph of sine, but shifted up 2 units. Oh, by the way, in case you didn't see that right away, I just want to rewrite it. This is the same as sine x plus 2. I know that seems silly for me to just do that, but maybe it's not so silly. This can sometimes help you see that, yes, this is sine x and then shifted up 2 units. If the 2 is out front, sometimes it throws people off, but, it's still just a plus 2. It's a positive 2. So to graph something like this, what you might do is you might do a little scratch work picture where you draw sine first. And I guess this is my first time calling it sine x, but we just said that's a different way of labeling it. Maybe draw that first and then shift up 2 units to get to your final picture. Final picture I'll make a little bit bigger. That's going to be our final answer. We want that to look good. Notice in the final picture I'm allowing myself a little bit more room up here because I know it's going to be shifted up. And we can call it the x-axis and we can call it the y-axis. So my first little picture over here is just like the graph of sine that we had earlier. And as you do these, you'll get pretty quick at graphing sine and cosine. So remember, we just said sine x is the one that passes through the origin. I know that by the time we get to 2 pi, it should be at the same height. Same thing with negative 2 pi. So you could start with those points. And then just remember, it waves up and down. It reaches a maximum height of 1, minimum height of negative 1. So you can draw this pretty fast. You don't need to do the unit circle all over again. You don't need to do that every time. So now in our shift up 2 units, maybe we'll have the same, 2 pi over here, pi. Well, I guess if you think about it, the original graph, the highest it went was a height of 1. So on the new picture, the highest that we're going to go is 3. On the old one, the lowest it went was negative 1. So when everything gets shifted up, I guess instead of passing through 0, 0, we pass through 0, 2. Maybe I'll start with those same 3 points. Shift it up 2 units. These 3 points are now up here. Could also do a little dot here and a dot here. I know it's going to touch those points, and then I'll kind of complete the graph. So we know the overall shape. We have it right here to reference. We're just shifting it up like that. Like that. And when you draw this, do the arrows, like an arrow on the right to indicate that it keeps going, and an arrow on the left to indicate that it keeps going. And that's a really good graph. So that was 2 plus sine x. So just to be clear, this is the final answer. When you draw any kind of trig function, you should always make sure that you draw at least one period. Remember, a couple of pages ago, we said that the period is 2 pi. So what I mean by that is one complete version of the shape, and I kind of did 2 periods in this picture. So why don't you take a minute and try part B, and this is a good spot to pause the video, try this, and then check back with me. All right, so for this, I think I'll start with a picture of cosine x. This one's called G. And then we're applying a graph transformation to it. The negative means we're going to reflect vertically. Again, that's talked about in that appendix in the back of the workbook. So this is a good spot to do a little practice picture of cosine. All right, so we said cosine starts out at a height of 1. I mean, I said starts out. I'm talking about the y-intercept. I usually kind of start here, and then I go to the right. So, yeah, thinking of it up here at a height of 1. By the time we get to 2 pi, it needs to be back up at a height of 1. And if you went left, negative 2 pi, you're also back up at a height of 1. So from there, if you know the overall shape, you might be able to fill this in. So we want to take this picture and flip it vertically. So instead of a y-intercept of 1, this one will have a y-intercept of negative 1. So I'll put a dot down there. So I do think it helps that we drew cosine first so that we can refer to it as we flip it. Let's have, I guess, a point up here and here. And now I'm ready to sort of fill that in with the nice smooth curve. Again, try not to do sharp zigzags. Think of it more like a roller coaster that sort of gently goes up and down. Not a lightning bolt. Okay. Yeah, that's a good picture. So this is negative cosine x. So far we've focused on sine and cosine, and the truth is sine and cosine are the most important, but we also want to talk about the other ones. I'll go through the other ones a little bit quicker, maybe. So we want to talk about tangent and cotangent. We're going to do those together. First of all, there's a question for us. If a value of t has a terminal point of xy, what is the terminal point of t plus pi? So I'm going to draw a unit circle here. And this question is more of like a general question. It didn't give us a specific value of t. just means in general. So maybe I'll imagine some value of t like this that takes me to some terminal point, x comma y. And the question is, what is the terminal point of t plus pi? Well, remember, 2 pi goes all the way around, which means pi goes halfway around the unit circle. So if I add another pi to this, this is sort of what a plus pi looks like. It takes me to a new terminal point, but that new terminal point is sort of on the opposite side of the planet from the original one, because it's a circle and it's symmetric. So because of that, the terminal point that we get to is sort of the flipped version, and I could say this is negative x comma negative y. So that's sort of the answer to this question, is negative x, negative y. Now, we know that tangent is defined as y over x. So what I want to add to our notes is tangent of t plus pi would be that y value, which was negative y, over that x value, which was negative x. But a negative over a negative would cancel, so this would get you y over x. So we just said tangent of t plus pi equals y over x. We have a conclusion. We have a therefore. Therefore, tangent of t plus pi is getting us the same thing as tangent of t. That looks like something we said on the first page of this section when we talked about sine and cosine, except with sine and cosine there was a 2 pi, and it looks like with tangent there's just a 1 pi. So our result is tangent and cotangent are periodic with a period of pi, meaning they repeat themselves every pi units. And the same is true for cotangent. Cotangent would look like what we just did, but with x over y instead. It's the flipped version. And we could also rewrite this in terms of x if we wanted. If you replace the t's with x's, it's still true. So we might use that to help us with the graph on the next page. Now I'm thinking when we graph tangent and cotangent, they somehow need to repeat themselves every pi units. So this time, I think we'll do a little table of values. And, let's do kind of a column for x, a column for tangent x, and leave a little room for scratch work off to the side. So some of the ones that I want to show you are 0, pi over 6, pi over 4, pi over 3. Those are some of the values we've seen on the unit circle. Another one that we've seen is pi over 2. I'm going to leave a gap here. There's a reason for that. I want to fill something in there afterwards. So this is my table of x values, and we could find each one of these with a little scratch work. So tangent of 0 would be sine of 0 over cosine of 0. Which is 0. Okay? So we'll graph this at the bottom of the page in a minute, and we'll have the point on the graph 0, 0. This one, I do think it's helpful to use what we know about sine and cosine to help us. So this would be 1/2 over square root of 3 over 2. There's a couple of ways we could simplify this. Right now, because I know what we're working on is we want to graph this. This is square root of 3 over 3. I'm going to say as a decimal, I found this with a calculator to be around 0.58. I think that's going to help when we get to graphing it, so I'll write it that way. Next up, tangent of pi over 4. This is square root of 2 over 2 over itself. A number over itself is 1. This one, I'll skip the scratch work on this just for the sake of time and say that if you did tangent of this, you're going to get the square root of 3. And the square root of 3, if you do that on a calculator, is roughly 1.73. Now, already this makes it seem like the graph is pretty different from sine and cosine, because with sine and cosine, the largest value we ever got was 1, but for tangent, it can go larger than that. By the way, I also found this as a decimal is roughly 1.05. This as a decimal is roughly 1.5708, in case we need that. If you try to find this one, you get 1 over 0. So 1 over 0 is undefined. So something is going on here with this graph, because sine and cosine didn't have any places where they were undefined. You might remember back in 2.2, I think at some point we talked about domain and range, and yeah, there are some places where tangent and cotangent can be undefined. This is one of them. Now, do we have enough points to make a nice picture out of this? I think I'm going to show you a few more points that I found in between here. That's why I left a gap. And I found these with a calculator, so I cheated a little bit. But I thought, if this is 1 point, like if you look at the points we have, it looks like they're growing, right? Starting at 0, and then they get bigger, 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 and then undefined. So you might say, what happened in between here? So you might get curious and try some points. I tried 1.5, and I got, we're going to do 3 points here. I got, on a calculator, this is around 14.10. So it's getting pretty large. Then I did 1.55. And on a calculator, this got me 48.08. And I thought, well, this one's around 1.5708. So I want to get close to that and see what's happening when this thing becomes undefined. What's happening near there? So I did 1.57. I'm really close to that. And my calculator told me 1,255.77. So on these values, I think we're growing larger and larger, and then it's undefined. Let's move to the bottom of the page and draw some of this. Now, I think I'm going to show you graphs of both of these. Maybe what I'll do is swap to a page where I already have it drawn. Okay, I just did a little movie magic there, and I switched to a page where I already had these drawn. So I did use the values we found in the table above, if you look closely at it. And what's happening is we said that when you put in a 0, this is the graph of tangent, by the way. This is tangent and cotangent. 0, 0 was a point that we were expecting to see, and there it is, passes through the origin. And then as you go to the right, we saw that it was growing steadily. And the closer we got to pi over 2, the larger it got. It even went over 1,000. So I draw the arrow pointing upward like it's getting larger and larger. This is a vertical asymptote. You probably learned about asymptotes in an algebra class, probably not when not having anything to do with trig, but other kinds of functions have asymptotes also. The idea is that this arrow is getting closer and closer to this dotted line, but it never quite touches it. And then if you were to try values that are negative, you would see it getting smaller and smaller and approaching this dotted line, where tangent would be undefined at that dotted line. And then we know the period is pi, which means if we have a part of the picture that has a width of pi, that part of the picture just copies itself over and over again. So it's this shape kind of copy and pasted over and over again forever. Cotangent would be very similar. We're not going to do the whole table and everything for that one, but it makes sense that cotangent and tangent are closely related. They are reciprocals of each other, so you get something similar happening here, except this time the vertical asymptotes are happening at x equals 0, x equals pi, x equals negative pi. So it's kind of flipped and offset a little bit, but similar idea. So let's get to the next page here. All right, so we'll also do, I guess, secant and cosecant together. I have some notes to put here. These two things, we called these reciprocal relationships, and we can use those to help us figure out the graphs. I'm telling you here in a note that they do have the same period as sine and cosine. Let's find some values. By the way, if I find some values, I could set this up as a table. What I really want to show you is how you can use what you know about sine to help you figure out cosecant. So for example, sine of pi over 6, we said is 1/2. That's one of those common values we know. That means cosecant of pi over 6 is 2, because it's the reciprocal. We know sine of pi over 4 is the square root of 2 over 2. So cosecant of pi over 4 is the flipped version of that. You know that we usually don't like to leave a square root in the denominator. The way that you would fix that is you could multiply this by square root of 2 over square root of 2. And if you do that and do the canceling, I'll show you the canceling. This is a 2 over 2 that I want to cancel, so I get square root of 2, which, by the way, is around 1.4. Another common sine value is for pi over 3, you get square root of 3 over 2. Therefore, cosecant of pi over 3 is the flipped version of that. I would do the same kind of algebra trick to help with cleaning this up. 2 square root of 3 over 3. So this time the 2 and the 3 don't cancel. You just leave it like this. All right, and let's do one more. Okay, so for this one, cosecant of pi is, well, when you do the reciprocal of it, this one is undefined. All right, so we could keep going with this. We could set up a table of values of cosecant or a table of values of secant and, draw the graphs from there. Instead of doing it that way, here's what I want to show you. First of all, I'll tell you that this undefined one, this is also going to be a vertical asymptote, kind of like we saw with tangent and cotangent. So for this picture, I kind of want to have room for both of these. Cosecant on the left, and then we'll do secant on the right. Let's do x-axis, y-axis. Let's kind of put 2 pi over here. Now, what we just saw above is that there is an undefined one at pi, so I could make a vertical asymptote there. I'm going to do this a little bit different. There's something I want to show you here. if you have two colors to write this in, it would be nice to do that. I think on top of our graph, even though we're graphing cosecant, I want to show you how it is related to sine. So I'm going to maybe grab a pencil here if I have one, and I'll do kind of a quick sketch of sine x. It'd actually be nice to do this in pencil, and then like potentially we could erase this afterwards, but I'm going to use this as kind of a guide. So just to be clear, this is sine x. All right, now if you're wondering how is he going to use that as a guide, what does that mean? Well, I've already drawn a vertical asymptote here, and you notice that sine x is touching a height of 0. Well, that's kind of when we got the 1 over 0. We got a vertical asymptote. Well, it turns out that that's going to happen anywhere that sine is at a height of 0, we would have a 1 over 0. So you can use that as a guide for where the vertical asymptotes go every time sine touches the x-axis. So that's one thing. All right, another thing is every time sine is at a height of 1, this is my height of 1, this is my height of negative 1, every time it's at a height of 1, the graph of cosecant would be the reciprocal of 1, right? But 1 over 1 is 1, so you could just put a dot there, and also here. And then at the negative ones, you would have the reciprocal of negative 1 is also negative 1, so you could do that. Why don't I go ahead and put a height of 2 on the picture, 2 and negative 2. All right, so this next part is a little trickier, is anywhere that sine x is at a height of 1/2, cosecant should be at a height of 2. So maybe I'll say this looks like a height of 1/2, so I need a point up here at 2. And I think we have another one about here, and do that. We could do the same thing here. Same thing with the negative 2's. Negative 1/2 becomes negative 2. So we could find more points, and we could use some of the other ones we found at the top of the page, but I think what I'll do is connect these dots with a nice smooth curve and say cosecant x approaches the asymptotes, right? You have to approach the dotted lines, but it never quite touches them. It actually swoops down like that, goes back up because it can't touch that asymptote or cross it. And then down here, it's doing kind of a flipped version of that. Now, at the top of the page, we said that cosecant and secant have a period of 2 pi. So what I've just drawn is everything sort of from x equals 0 to x equals 2 pi is this shape. It has two parts to it, but this shape needs to sort of be copied over here. And you would keep copying it to the right and to the left, and you just get more and more copies of this shape. And, you know, when I drew sine x, I said maybe afterwards we would erase it. Let's see if my eraser works. That was just kind of a guide. The black curve that I made is really the graph of cosecant. Good enough. So I think what I might do is switch the page to one where I've already drawn the graph of secant just to save a little time here. But same idea, except instead of being based on sine x, secant is going to be based on cosine. All right, here's my graphs. So now you can see my cosecant x and my secant x. And they also have a similar shape to each other, right? I mean, we were probably expecting them to be similar, and they're closely related, just like sine and cosine are closely related. So as we're sort of wrapping up this section, what do I want to say here? We looked at graphs of all 6 trig functions, and in the middle of the section, we did some graph transformations on sine and cosine. So I'm not going to ask you to do graph transformations of these other ones. I would say graph transformations for sine and cosine only. Those are good to know, like the vertically flipped one or shifted up 2 units, that sort of thing. When it comes to secant, cosecant, I would like you to know these graphs, like maybe just be able to draw these graphs as they are, but I'm not going to ask you to do like a flipped version on a quiz or a test or anything like that. So yeah, I guess that's about it. Don't forget there's also practice exercises at the end of the section. You can work on those on your own. And, as always, feel free to let me know if you have any questions.